Okay, now we're going to take a brief look at the issue of aberrations. What is aberration? What is an aberration? Well, it's a distortion of the image due to the imperfection in the design of an optical system. Okay, two typical sources of aberration. One is called spherical aberration, the other is called chromatic aberration. What is the meaning of spherical aberration? Well, it has to do with spherical lenses. Okay, if you draw a spherical refractive surface, you know, you write 1 over p plus 1 over q is 1 over f. If this equation were exact, then for any given p, you will get an exact image focused at a distance f, a q, behind the lens, right? So there will be no aberration. But the problem with it is that this formula itself is only an approximation. Why? Because it relies on the fact that parallel light rays will focus at an exact distance f behind the lens. That point, of course, is the focal point. But that is only itself an approximation. Right? It's an approximation. It relies on an approximation that the light rays are pretty close to the optical axis. We call them near axis light rays. Okay? So if you're looking at a large spherical refractive spherical surface, either by joining a mirror or a lens, then you find that, let's say a mirror, for example. Okay, this is part of a sphere. Right? Here's the optical axis. Now, here is the focal lens, focal point. You will find that beams that are close to the optical axis will indeed focus very well. But another beam that is not that close to the optical axis, that beam is not going to focus exactly at that location. It's going to focus somewhere differently. Okay, another beam that is further away may focus somewhere there. Okay, so you're going to lose sharp focus for beams that are further away from the optical axis. That is because the spherical design is not perfect. If you want a perfect reflective surface where all the parallel beams focus exactly at that one location, you're going to use a parabolic surface. Okay, so this is an example of spherical aberration. The same thing happens for spherical lenses as well. Now, what about chromatic aberration? Chromatic means having to do with color. Different colors correspond to what? Different frequency. And different frequencies will give you different speeds. Okay, because the index of refraction is different for different frequencies or different wavelengths. And because the index of refraction is different colors or different frequencies, beams will then focus, will travel at slightly different angles. Okay? So, you know, if you have a lens like this, okay, if you have a lens like this, then you have different colors coming in, say the red color. The red color has the longest wavelength, so it travels the least number of wavelengths inside the glass, so therefore it's going to be deflected with the smallest amount. Yet a blue one, on the other hand, comes in the same angle. It's going to be refracted a little bit more. Okay, of course, I'm exaggerating. Okay, so if this is the optical axis, okay, then you find the red color is going to focus here, and the blue color is going to focus there. All right. Now, suppose this is a camera lens, okay, with all the multicolor light coming in. And my question is, where are you going to put the film? Okay, I'm going to put the film here. You put the film here, you get a sharp focus for the blue light, you're going to lose focus for the red light. And if you focus there, then you can lose sharp focus for the blue light, even though you retain the correct focus for the red, for the red color. So this is a problem. It's called chromatic aberration. Okay. So to make these aberrations smaller, to minimize those, we have to do certain things. For example, to correct spherical aberration, in a real camera, oftentimes the lenses are aspherical. They're not exactly part of a sphere. This is designed to minimize the problem. But another issue is that with a camera, there is something called f number. Okay, like f11, f16. You know what that is? That is how big an opening you have for light to go through. The bigger the f number, the smaller the opening. Okay, the smaller the opening. So let's say f16, for example. You're using a very small part of the lens near its center. If you use only a part of the lens near its center, you don't have as much aberration, as much spherical aberration. The light rays will focus better. Okay, that is why I don't know if you probably have that experience. If you shoot a scene with a camera under broad daylight, okay, when the illumination is very good, then the lens doesn't have to doesn't have to open very wide. You can only use a small portion of the lens. Still, there's enough light to go through. Advantage of that is that only the central part of the lens is being used. There is less of a distortion. You will see an image more clearly. Okay. On the other hand, if you shoot a scene at a low light situation, you have to open up the lens wider. You cannot use f16, for example. You probably have to use f8 or even f5, 5.6, and so on. The lens will open wider. More light can go through. That is the advantage. But the disadvantage is that you're going to have more spherical aberration, so the image will not be focused as sharply as before. You're going to lose what's called depth of view, or depth of field. Okay, and with chromatic aberration, one way to correct that is to use materials with much smaller dispersion. In other words, those are materials whose index of refraction does not depend sensitively on the frequency. Okay, so those are issues that we have to address if you say were to manufacture a lens for a camera. You want to minimize all sorts of aberration, especially spherical and chromatic aberration. Okay, as the last important topic of this chapter, let's look at the mechanism of the eye. Of course, this is only from a physicist's point of view, so there's no detailed discussion about physiology, just the simple physics side of the story. Our eye basically consists of two important parts. One is a lens. Okay, this is just it's a conversion lens, and then this is the eyeball. In the back of the eyeball, we have a neural network called the retina. Okay, as light comes focused on the retina, the neuron tips at the retina will then turn these light signals into electrical signals, pulses, to be processed by your brain to interpret as images. Okay, now this lens roughly satisfies the same equation: 1 over f equals 1 over p plus 1 over q. Our eyes can focus automatically. Okay, at least a normal eye would do that. That is, no matter where the object is, no matter what p is. You can always satisfy this equation so that this distance between here and there is q. Okay, the distance between the lens and the retina is q, so that you can see a sharp, image no matter where the object is. Now this is really remarkable because now what if f cannot change? If f cannot change but p varies, shouldn't q be variable as well? So in other words, the distance between the retina and the eye would have to change, right? Would have to change. And the question, how does it do that? Okay, how does it do that? Well, in reality, there are muscles around the eyeball, and these muscles, for a far, if you're looking at a very far object for a normal eye, the muscles are relaxed, the eyeball is not getting compressed, the lens is not getting compressed, and this distance is designed so that it is in fact equal to the focal length of the eye. Okay, so it's totally relaxed. P equals infinity, Q equals F, and that's why when you look at a distant object, you will not be straining your eye. Okay, on the other hand, if you bring the object closer and closer and closer, so P is smaller and smaller and smaller, then Q has to be greater and greater and greater if F doesn't change, right? So on the one hand, you have to compress the eyeball somewhat to make this Q distance a little bit longer. And on the other hand, in the real eye, the muscle contraction can also make the focal length change a little bit. They can make the focal length a little bit shorter so that the eye becomes a stronger focus, you have a stronger focus length. So, the combination effect is that you can still focus a close object sharply here on the retina. This is what happened to a normal eye. So you see, when you look at if you want to see something up close, your eye will be under strain. Okay, the muscle will have to compress the compress the lens in the eyeball somewhat so that you can see satisfy this equation, even for a small value of p. Okay, now there are two common defects associated with the eye. One is called nearsightedness or myopia. The other, as you know, is called farsightedness or hyperopia. In a nearsighted eye, you have no problem seeing something up close, but you have a problem seeing something that's farther away. Okay, most of nearsightedness are acquired. In other words, you're not born nearsighted. Just just as you age, you read a lot of books under the wrong type of light condition. Your eye gets strained too much, eventually becomes nearsighted. Okay, in the case of nearsightedness, probably what happens is that a person reads something or otherwise look at something up close for too long, so the eye is under a lot of stress, okay, and a lot of strain over a long time. So there is a permanent deformation, okay, of the eyeball and of the lens to some extent. So here I have a highly exaggerated picture, okay. So the eyeball is permanently longer because you want to focus something, further away, okay. You want to increase Q, right? You want to increase Q because P is smaller. Okay, this will have no problem if you put an object up close. It's going to land somewhere here perfectly, okay? So a nearsighted person has no problem seeing something up close. But if you want to look at something farther away, the focus of this will be shorter. So it's supposed to be focusing here, but your eyeballs are deformed, okay? So it's going to focus, instead of here, it's going to land on retina somewhere there, and that's a blob, not a sharp point anymore. That is nearsightedness. Okay, so it's a permanently deformed eyeball to some extent. Now, over to farsightedness. Regardless of your vision condition when you're young, when you're old enough, everybody will develop farsightedness. What's going on in farsightedness eye? Well, it's called hyperopia. This is when, with age, the muscles lose elasticity. Okay, so they cannot compress the eyeball as readily as they would when the eyes are younger. Okay, now you don't have to compress the eyeball when you look at something further away because the eye is relaxed. Okay, but when you read something, when you look at something up close, P is small, so Q has to be large. You have to compress the eyeball like this, but the muscles are tired or they're old. Okay, they lose elasticity, so they cannot compress it as much to that point, so that you're going to focus here, yet your retina is there, so you get a blob instead of a sharp point. That is what's called farsightedness. Okay, and the way you correct these vision defects, of course, the primary way is still wearing glasses. Here is an example how you might correct nearsightedness by wearing glasses. A nearsighted person has no problem seeing something up close, but you have problem seeing something afar. All right, now let's say without glasses, suppose you wear glasses, okay, take them off now. Take them off now. Okay, what I want you to do is, without the help of glasses, I want you to take a book or something up close, and I want you to put it in front of you and go further and further and further and further away until at some point you say, okay, I cannot see it clearly anymore. So there is a certain distance beyond which you cannot see things clearly. That distance is between here and there. So if you put an object this far or closer to your eye, you will be able to see it, right? But an object further away from that point, you cannot see it. So the way you correct that problem is by wearing eyeglasses. The pair of eyeglasses you wear are made of divergent or negative lenses, okay, or concave lenses. A concave lens forms a virtual image, right? So let's say I have a very distant object casting parallel light rays. Going through this lens, this eyeglasses, they're going to form a virtual image here. Alright, so the reason why you wear these glasses is that you want to turn a distant object to its image at that point, which is close enough for your eye to see. Okay, this is why we wear divergent lenses to correct nearsightedness. So suppose that distance, the distance that you can see clearly in front of you without glasses, it's, let's say 40 centimeters. Okay, let's say 40 centimeters or 0.4 meters. Okay, what kind of eyeglasses should you wear? First of all, it's a divergent lens, and secondly, you want to make sure that the distance between your eye and the image of a distant object would be about 40 centimeters, right? Because you can see 40 centimeters with no problem. All right, now there is a small distance between your eye and the glass itself. Let's say it's a centimeter. But roughly speaking, between here and there, you get about 40 centimeters, right? That means, roughly speaking, the focal length of that lens should be what? Negative 40 centimeters. So F should be negative 40 centimeters, roughly. Or roughly, negative 0.40 meters. Okay, now one can, when you look at the prescription of your lenses, of your glasses, you don't see these numbers. Rather, you will see something like 325 or 400. What do these numbers mean? Well, actually, these numbers refer to the power of the lens. Power of the lens. Okay. The shorter the focal length, the greater the ability of the lens at stopping or at bending the light rays. Okay, so therefore, I'm going to define power, D, as 1 over F. The shorter the focal length, the greater the lens power. The measurement, of course, is given in 1 over meter, right? Because F is in meters. But 1 over meter is kind of awkward, so we give it another name, we call it diopter. Diopter. 1 diopter is defined as 1 over meter. So, and we use the letter capital D to denote it. So if a certain lens is 1 diopter, you know what that means? It means the focal length is what? 1 meter. What about 2 diopters? So 1 of F is equal to 2 diopters. That means F is equal to what? 50 centimeters, or half a meter. Okay, what about 10 diopters? Then F equals 1/10 of a meter, or 10 centimeters. Okay, that's a shorter focal length, therefore a more powerful lens. So, in this case, if the focal length is negative 0.4 meters, what is the power of the lens? D would be equal to negative 1 over 0.4, right? And we know what that is. That's negative 2.5 diopters. Okay, and that is what you see. If you see in your prescription, it says the lens is negative 2.4 or sometimes 250 depending on the unit they use. That means the focal length is negative 0.4 meters, and what that means is that you can see an object placed up to 40 centimeters in front of your eye or closer without any extra help. Suppose your nearsightedness is more severe, so you can only see an object placed at 20 centimeters in front of your eye without any vision aid. Then the focal point has to be here, right? Because you have to bring the object here, 20 centimeters instead of 40 centimeters. And then the power of the lens will be negative 1 over 0.2 instead of 0.4. So that will be 5 diopters, or negative 5 diopters, or negative 500. You're going to see your prescription like that. So with that, you have an idea how to prescribe glasses for yourself, at least roughly. At least these prescription numbers will make sense to you. Okay, will make sense to you. Of course, for farsightedness, how do you correct that? Well, you have to use a positive lens instead of a negative lens, but the idea would be similar. Then, of course, these days we also have what's called laser vision correction. How do these work in principle? Well, the laser vision correction works by reshaping the shape of the cornea or the lens. This is the lens. Okay, with a nearsightedness, the problem with nearsightedness. Here's nearsightedness, right? You see, the focusing is too premature. You want to focus here instead of there. This lens is obviously too powerful. It's too powerful. Okay, it focused the light too short. You want to focus it there, and the way to do that is to make the lens flatter. Okay, see, the more curved the lenses are, the more powerful they are. But in the case of a person with nearsightedness, this lens is too powerful. So what you do is you use the laser. Okay, use what's called an XMR laser to reshape the cornea so that it is not as bulged out as it is now. It's slightly curved. It's less curved. It's less curved. Okay, so you have to burn away a layer of the cornea so that it is flatter. And this is all computer controlled. The computer measures the curvature of your lens, and it knows exactly how much to cut away so that you will get a perfect shape so that the lens is okay. You cannot change your eyeball, but the lens is flatter so that this beam will focus here instead of there after you lower the power of the lens. Okay, so that's how laser vision correction works in principle.